One of the most useful ways to analyze a circuit is to look at the relationship between voltage and current. And there is one component that makes that analysis very simple. This is the resistor. Its function is very simple. It restricts the flow of electrons. Now, impeding current may seem a little silly, but there are times you may want to reduce the current flowing to a component or lower the voltage going to some sensitive electronics. In an ideal world, the resistor creates a linear relationship between current and voltage. And if you know two of those three things, voltage, current, and resistance, you can easily calculate the third. We'll see how to do that later, but for now, let's see how a resistor works in a circuit. In the previous episode, I showed how moving current can be represented by steel balls in a tube. If one steel ball represented one electron, then it would take around 6.25 times 10 to the 18th steel balls to move past a point per second to make 1 amp. Since I don't have billions of steel balls in a massive plastic tube, we need some other way to show electric current. As it turns out, fluids like air and water actually make a pretty good representation for electric current. What I've got here is a circuit, not of electricity, but of water. I've added some mica powder and blue food coloring to it so you can see the water flowing more easily. In our little demo, the pump represents a power supply like a battery or a wall adapter that pulls water up from a well and gives it the push needed to move around the circuit. The tubes are like wires. They provide a path for the current. The water pressure in the tubes corresponds to voltage, and the amount of water moving through a tube corresponds to electrical current. Note that we're using conventional current, so the water is flowing from high pressure to low pressure. Amperes is coulombs per second, so in terms of water, that would be volumetric flow rate, something like cubic centimeters per second. What we've got here is the water analogy of a resistor. This is some steel wool shoved into a tube. You can see how all that material resists the flow of water, and there is higher pressure on the side the water is entering the resistor. The same holds true in electronics. There is a voltage difference between the ends of the resistor when current is flowing through it, and this is known as a voltage drop. Let's go back to the actual resistor component. If you were to slice one open, you would find coils or film of tiny wire or a solid core made of a carbon mixture. However it's made, the resistor acts to impede current. In 1825, the German physicist and mathematician Georg Ohm began experimenting with early chemical batteries and thermocouples to produce voltages. By varying the size of wires used to complete the circuit, he determined that voltage and current were proportional. In math terms, that means the voltage between 2 points is equal to the current flowing between those points times some number, and that number is known as the resistance between those points. Ohm's law is often written as V equals IR, or voltage is equal to current times resistance. Lucky for Mr. Ohm, the unit for resistance was named after him. The ohm is abbreviated with the Greek letter omega. With this information, we can begin to analyze circuits. As an example, we'll connect a resistor to a power supply that provides 3 volts. The electronic symbol for a resistor is a zigzag with 2 terminals. It represents a more complicated path and therefore reduced current flow. Note that it doesn't matter which way we connect the resistor, it will do its thing regardless of orientation. We will connect the terminals of the resistor to the positive and negative terminals of a power supply that's been set to act as a voltage source. A voltage source, similar to a battery, will supply as much current as needed to maintain a particular voltage between the terminals. Now that we have a circuit, current will flow from the positive terminal of the voltage source through the resistor and back to the negative terminal. The power supply will be set to 3 volts, and it will also tell us how much current it is supplying. With that information, we can determine the resistance of the resistor. Let's try it. Alright, I've connected the resistor to this power supply using some alligator clip leads. You'll notice I used red for positive and black for negative terminals connected to the power supply. When I turn it on, it reads about 3.03 volts. And it also tells me that about 0.03 amps are flowing from the positive terminal through the resistor and back to the negative terminal. Let's see if we can use this to calculate the resistance of this component. Using Ohm's law, V equals I times R, we can plug in the values from our readings. So 3 volts equals 0.03 amps times R. Using a little bit of algebra, we can calculate R. And we get R equals 101 ohms. Now that we've mathematically determined that we have a 101 ohm resistor, let's check our work. This is a digital multimeter, and it's one of your best friends when analyzing a circuit. Most basic models can do things like measure voltage, current, and resistance. We'll set this one to measure resistance and touch the leads to the ends of the resistor. As you can see, it's reading about 100.2 ohms, which is pretty close to our math results. Since this is labeled as a 100 ohm resistor, we'll call it good enough. If you're wondering why the measurements and calculations didn't come out to be exactly 100 ohms, that's because there are inconsistencies in the manufacturing of resistors, which of course means that the resistance can be a little bit off from the listed value. Additionally, there's resistance in the wires and potentially the power supply itself, so measuring the voltage between the terminals of the power supply could be a little bit different than measuring the voltage between the terminals of the resistor. Back to our water demo, we see that the steel wool, much like the resistor, restricts flow. If we were to add an even denser material like a sponge, the water flow would decrease even further. The same holds true in electronics. For a given voltage, as resistance increases, current decreases. Knowing Ohm's law by heart, V equals IR, will get you through many troubles in the electrical world, so it's one of the few equations I recommend committing to memory. Besides, it's only 3 letters. As it turns out, by resisting current, electrical energy gets converted to heat. In the next episode, we'll learn how to calculate electrical power and figure out how to do something useful with all of that heat from resistors.